Assalamu alaikum. Today we want to talk about chapter 9, part 2 in molecular geometries. Remember last time we talked about this sample exercise and we learned how to use the VSEPR model to predict the molecular geometry of O3, and that was the arrangement of 3 electron domains is trigonal planar, and that from table 9.1. Whereas the molecule has a bend shape, and that's from table 9.2. And for the second molecule, SnCl4, we draw the Lewis structure, and then we found that the resulting electron domain geometry is tetrahedral, also from table 9.1, and the molecular geometry is trigonal pyramidal from table 9.2, like that of an H3. And also you can see this practice exercise, predict the electron domain geometry and the molecular geometry for SeCl2 after drawing Lewis structure and using tables 9.1 and 9.2. We determined that the electron domain geometry is tetrahedral, whereas the molecular geometry is bent. For CO3-2, the electron domain geometry is trigonal planar, and the molecular geometry is also trigonal planar. Now we want to talk now about the effect of non-bonding electrons and multiple bonds on bond angles. Now we can refine the VSEPR model to explain slight distortions from the ideal geometry summarized in table 9.2. For example, consider 3 molecules, methane, CH4, ammonia and H3, and water H2O. All 3 have a tetrahedral electron domain geometry, but their bond angles differ slightly. And notice that the bond angles decrease as the number of non-bonding electron pairs increases. Here the bond angle is 109.5, typical tetrahedral, because this lone pair pushes here, the angle becomes smaller, 107, and here we have 2 electron pairs, they push more on this angle, or electron repulsion, of course, 104.5. Now, if we look at this figure, shows us the relative volumes occupied by bonding and non-bonding electron domains. Now, C, bonding electron pair and non-bonding pair. Since non-bonding electron pairs, as you can see, take up more space than bonding pairs, as a result, electron domains for non-bonding electron pairs exert greater repulsive forces on adjacent electron domains, and this will tend to compress the bond angles, as we saw in the previous example. Now also multiple bonds affect bond angles. Now let's look at the Lewis structure of molecule called Phosgene. You see, this is Phosgene. Now, double and triple bonds place also greater electron density on one side of the central atom than do single bonds. So as a result, you see that electron domains for multiple bonds exert a greater repulsive force on adjacent electron domains than do electron domains for single bonds. And here you see this bond angle increases, and also this increases, and this one decreases from the typical 120 of trigonal planar geometry. Okay, then therefore they also affect bond angles. Now molecules with expanded valence shell. Now atoms from period 3 and beyond may be surrounded by more than 4 electron pairs. Molecules with 5 or 6 electron domains around the central atom have molecular geometries based on either trigonal bipyramidal 5 domains or octahedral 6 domains electron domain geometry, and we will see this in table 9.3. Now, if we look at this figure, which shows us in a trigonal bipyramidal geometry, there are 2 types of positions for the outer atoms. we have 2 axial, where the bond angle is 90, and 3 equatorial, where the bond angle is 120. Of course, placing then any non-bonding pair will be in the equatorial position because this is more stable than putting them on the axial position because they are far from each other. So if we have one electron pair, we put it here. The second electron non-bonding pair, we put it here. A third one, we put it here. We avoid placing non-bonding pair on axial position. This will destabilize the molecule due to electron repulsion. So remember, we have 2 axial and 3 equatorial, and this is the bond angle for them. So let's go to this table 9.3, trigonal pyramidal electron domain. We start with total electron domains 5, then there are 4 distinct molecular geometries in this domain. Bonding domains 5, non-bonding domains 0. So we have here AB5, like example PCl3. This is called trigonal bipyramidal. If we have 4 bonding and domains and 1 non-bonding, like in SF4 we have, this is called CISO. If we have 3 bonding pairs and 2 non-bonding domains, like in ClF3, then we have T-shaped. And if we have 2 bonding domains and 3 non-bonding domains, then we have, like in XeF2, we have linear. So these are the molecular geometries for a compound with total 5 electron domains. However, if we look at the octahedral electron domain, all positions are equivalent in octahedral domain. If we have 6 bonding and 0 non-bonding, we have octahedral, like in SF6, 5 bonding, 1 non-bonding, square pyramidal, like PRF5, 4 bonding and 2 non-bonding, like XeF4, we have a square planar. Then, as I said, there are 3 molecular geometries: octahedral, square pyramidal, and square planar. Now let's see this sample exercise. Use the VSEPR model to predict the molecular geometry of SF6. Draw Lewis structure as we learned and place all the atoms around the central atom so that you have lower energy conformation result from having non-bonding electron pairs in equatorial. As we said, we always put the non-bonding electron pair in equatorial because this will give us lower energy conformations. We have the trigonal bipyramidal electron domain geometry because we have 5 domains. But since we have 4 bonding and 1 non-bonding, then we have the molecular geometry of SF6 is CISO. Now let's look at shapes of larger molecule. Example, acetic acid, CH3COOH. In larger molecules, we can use the VSEPR model to predict the geometry about each atom. Makes more sense to talk about the geometry about a particular atom rather than geometry of the whole molecule. So after drawing Lewis structure, we have 3 central atoms, as you can see here. So for this one, we have 4 bonding domains. So we have electron domain geometry is tetrahedral. Here we have 3 bonding pairs, again trigonal planar. Here we have 1, 2, 3, 4 electron domains, also tetrahedral. But what about the molecular geometry? If we add here, for example, molecular geometry, tetrahedral, tetrahedral, trigonal planar, but here tetrahedral bent. And the predicted bond angles are 109.5, 120 degree, 109.5. Now let's talk about molecular shape and molecular polarity. Recall that bond polarity is a measure of how equally the electrons in a bond are shared between the two atoms of the bond. As the difference in electronegativity between the two atoms increases, so does the bond polarity, as we talked about in chapter 8. We saw that the dipole moment of a diatomic molecule is a measure of the amount of charge separation in the molecule. For a molecule consisting of more than two atoms, the dipole moment depends on both the polarities of the individual bonds and the geometry of the molecule. For each bond in the molecule, we consider the bond dipole, which is the dipole moment due only to the two atoms in that bond. Consider, for example, the linear CO2 molecule here. The dipole moment of CO2 is 0, although even though the individual bonds are polar. The geometry of the molecule dictates that the overall dipole moment be 0, making CO2 a non-polar molecule. And you can see here in this figure the CO2 a non-polar molecule. Now consider water, a bent molecule with two polar bonds, as you can see in this figure. Again, the two bonds are identical and the bond dipoles are equal in magnitude. Because the molecule is bent, however, the bond dipoles do not directly oppose each other and therefore do not cancel. So by adding the individual bond dipoles, one can determine the overall dipole of the molecule. So the water molecule has an overall non-zero dipole moment and mu equal 1.85 dpi and is therefore a polar molecule. Now this figure shows some polar and non-polar molecules, all with polar bonds. The molecules in which the central atom is symmetrically surrounded by identical atoms like BF3, for example, and CCl4 are non-polar. For ABN molecules in which all the B atoms are the same, certain symmetrical shapes, linear, like AB2, trigonal planar AB3, tetrahedral and square planar AB4, trigonal bipyramidal AB5, and octahedral AB6 must lead to non-polar molecules even though the individual bonds might be polar. So here you can see ammonia and H3 is polar, HCl is polar, CH3Cl is polar because we have here in it dipole, whereas CCl4 is non-polar, and also BF3 is non-polar. Finally, let's look at this sample exercise talking about polarity of molecules. Now predict whether the following molecules are polar or non-polar. Now we start with PrCl. Chlorine is more electronegative than bromine. All diatomic molecules with polar bonds are polar molecules. Consequently, PrCl will be polar, with the chlorine carrying the partial negative charge. The actual dipole moment of Br as determined by experimental measurement is mu equal 0.57 d. Now the second SO2. Because oxygen is more electronegative than sulfur, SO2 has polar bonds. The resonance atoms can be written for SO2, remember, like this. For each of these, the VSEPR model predicts a bent geometry. Because the molecule is bent, the bond dipoles do not cancel, and the molecule we have here polar. Experimentally, the dipole moment of SO2 is mu equal 1.63 dpi. Fluorine is more electronegative than sulfur, so the bond dipoles point toward fluorine. Now the 6 SF bonds are arranged octahedrali around the central sulfur. Because the octahedral geometry is symmetrical, the bond dipoles cancel and the molecule is nonpolar, meaning that mu equal 0. This will end this part 2 and this chapter. Thank you.